Hello and welcome to this video on rotational motion. Specifically today we're going to talk about kinematics in a rotational reference frame and why do we even care. To start with, we'll talk about why we even care. Rotational motion isn't just objects moving in circles. We've talked about that, planets, satellites. What we're really looking at today is how do objects move when they're moving in any spinning thing. Now this could be circles, as we've discussed previously, such as a record player or a tire, and the motion of points on the record player or tire, so like the rotation of that point there or that point there. But it also is descriptive of how many other parts of our life work, from the circular motion of a wrench tightening a bolt, or the circular motion of someone tucking and rolling in a dive, or doing an axle spin in figure skating. Anytime something starts rotating, rotational motion starts applying, and a lot of the traditional methods we've been using don't work anymore. For instance, consider this record player. It's not a perfectly drawn circle, forgive me, but as this X and this triangle go around the circle, they travel at different speeds. The X has a much shorter distance to go, so it needs to travel at a lower speed to complete its revolution, as opposed to the triangle, which has to go all the way around. Now, the problem here is that these two objects are connected. They're on the same surface, but their speeds, or their linear speeds, what we typically refer to, are very different because of the different distances they have to travel. Further, they're constantly accelerating. In order to move in a circle, you have to accelerate. You have to have an accelerated motion. So in order for this to work, there's a constant acceleration, which means we need to factor that. We're constantly moving between x and y directions. The linear math we've used thus far isn't helpful. But if we look at it this a slightly different way, and instead of looking at the distance they travel, we instead look at the arc of a circle they travel through. While the distance from here to here that the x travels and the triangle travels is different, the angle, the fraction of a circle they complete, is the same. Because of this, whenever we talk about something moving in a circle or rotating, what we'll talk about instead of talking about the distance is we'll talk about the angle they pass through, or their rotational position. Rotational position is indicated with a theta. So the initial position where they start would be theta initial, or theta naught, and where they end up would be the theta they travel to. So the change in rotational position would be delta theta. So by talking about the angle they travel through, we can talk about points that are in the same line and on the same object and how they move without having to talk about different speeds and different relations. We can talk about them uniformly because the angle these two travel is the same in this case. If we want to go a step further, we can talk about their angular velocity, or omega. The angular velocity is how much of a circle they go through in a matter of time, or velocity, just using a different form of position. We can even talk about the angular acceleration, which alpha, which is the change in angular velocity per change in time. And all of these allow us to talk about the motion of an object in a circle in a way that is easier than talking about straight lines, constant accelerations, because all we care about is their motion along the circular path. Some notes on units. Because we're not talking about a distance anymore, because we're talking about the amount of a circle we go through, we use the units of radians to talk about our angles. One full trip around a circle, one full circle, is 2 pi radians. Now, radians themselves aren't a unit, they're dimensionless. This is a convenient tool that we can use later, we'll talk about, but effectively, there is no unit for how much of a circle you've gone through. It's just a number. And know that every 2 pi of them, every 6.28 and change, is a full revolution, which means that my omega, my angular velocity, is going to be in radians per second, which strictly means that the unit here is 1 over seconds, or seconds to the minus 1. My angular acceleration would be in radians per second squared, which, again, 1 over seconds squared, or seconds to the minus 2. Why do we do this? Why do we not use degrees, for instance, or gradients if you wanted to talk about engineering? Well, because if I want to talk about how fast something's going in a straight line, if I want to be able to relate this to things we've talked about previously, the way I can translate that is through the radius. The distance an object will travel here, the distance here, would be equal to the angle you travel through times the radius. If I multiply by the radius, which is typically going to be measured in meters, from here to here would be measured in meters, I need the units to match up. I need distance to be in meters, because that's what we measure distance in, but I also need the radius to be in meters, because that's, again, a distance. The only way to make that work is by having the angle be unitless, be dimensionless. Once you've got these terms in your head, the rest of the unit is exactly the same as the kinematics unit. Instead of talking about distance and displacement, we'll be talking about rotational distance and displacement. So instead of x, we're talking theta. Instead of talking about velocity, we're talking angular velocity. Instead of talking acceleration, we're talking angular acceleration. The terms themselves are only amended, but the concepts, the execution doesn't change. A common way for people to think about this is that whatever you're talking about linear, just replace it with the rotational symbol. So wherever you'd see x in a linear thing, distance or displacement is x, use a theta instead. Wherever you talk about a linear initial position, you talk about the rotational initial position. Whenever you're talking about your displacement, your change in position, you talk about your change in rotational position, or your delta theta. And these two are directly related by the radius. Your velocity and angular velocity are directly related by your radius. In other words, if I know the angular velocity here and I multiply by the radius, how fast this x is moving in a straight line would be equal to the radius times your angular velocity. Now that's going to change constantly because it's accelerating, but at an instant, it'll be that. The same is true with the acceleration. The acceleration of the object moving in a straight line, what we refer to as the tangential. This T means tangential. In other words, the acceleration of an object in this line here is going to be equal to the angular acceleration times the radius. To put it a slightly different way, if you were in a car going around a corner, your acceleration that you would experience in the car would be equal to the angular acceleration times the radius from the center of the circle. If you are moving at a constant angular acceleration, you perceive yourself moving at a constant speed. Well, there's still that centripetal acceleration we've talked about previously that's going to make sure you move in that circle. The speedometer in your car won't change. So how does this work? How does this translation help us? Well, let's say we have a car moving 60 miles per hour. That is its tangential velocity. How fast are the 14-inch tires rotating? Well, first, let's get 60 miles per hour in meters per second, so it's actually useful. 60 miles per hour is 26.82 meters per second. So this car is moving at 26.82 meters per second. If I'm keeping that constant velocity, how fast are the tires rotating? Well, 14-inch radius is 0.3556 meters. So using the relation I have here, Vt equals omega r. Or in other words, the 26.82 is going to equal omega times 0.3556. Divide the 3.3556 to the other side, and I get 754.22. And this would be radians per second. If we want to put this in slightly different terms, divide that number by 2 pi, and you're doing 120.04 revolutions, full rotations per second, when your car is going 60 miles per hour. This is a very high number, but it explains how tires wear and tear. Go ahead and give this one a try. How many rotations does a 14-inch tire do in 1 mile? 1 mile is, in this case, 1,600 meters. So how many revolutions does it do in 1 mile? Don't worry about the 60 miles per hour, that's velocity. Not what we're talking about. We're talking about a position, a displacement. Go ahead, give it a try. Check back after you're done. If you've done your math carefully, you should get 7,161.08 rotations. If you only got the radians value, remember, radians is not rotations. There's 2 pi radians to a rotation. So you have to convert.